Consider the task of in-hand cube rotation with a robot hand. We study the more challenging scenario when there are many different hand designs. To approach this, we present Get0, graph embodiment transformer for zero-shot embodiment generalization. Get0 is an embodiment-aware method that can control all of these hand designs with a single set of policy weights. We see that Get0 works even if we remove joints, extend links, or even a combination of the two. And the best part is that all of the highlighted hand designs were never seen by Get0 during training time. In the typical robot learning approach, we train separate policies per robot design. But suppose we need to remove a finger due to damage. Since these policies aren't aware of the robot's design, they can't adapt to new hardware changes. In contrast, using Get0 lets us control a range of similar robot designs with a single network by conditioning on the hardware design of a robot. With this setup, we can train a model using some hand designs, and then at test time, control a new design. To have an embodiment-aware policy, we need an embodiment representation. To do so, we present Git, or graph embodiment transformer. We start with the embodiment graph on the left, which has joints as nodes and links as directed edges. For each joint, we construct separate tokens containing local state and local hardware properties. These joint tokens communicate through the attention mechanism in the transformer to enable global coordination. Next, we use the embodiment graph as a structural bias in the transformer attention mechanism. The main idea is that each joint has an attention score with every other joint that we modulate according to how joints are connected in the embodiment graph. Finally, the output consists of a policy head for per joint actions and a self-modeling head that predicts the forward kinematics position of each joint. We find that forward kinematics is a useful metatask that improves cross-embodiment transfer. So how do we apply Get0 to the in-hand rotation task? We start by procedurally generating many different hand designs with various joints and links missing. For each of these designs, we collect separate embodiment-specific experts by using reinforcement learning and simulation. This covers the first two steps. Next, we distill demonstration data from these experts into an embodiment-aware Git model using behavior cloning. Finally, we deploy our model to perform zero-shot control of a previously unseen hand design. We evaluate the real-world performance of Get0 using embodiments not seen during training time. We observe that Get0 successfully controls a hand with a missing finger thanks to the embodiment graph encoding and self-modeling. We compare to a baseline which doesn't have these features and observe that it struggles to fully support the cube, leading to difficult cube positions that are hard to recover from. Despite never training on any link length variations, we observe that Get0 is still able to control a hand with link extensions shown in orange. In contrast, the baseline has trouble coordinating the fingers and pushes the cube off of the hand. We observe failure cases. On the left, the cube keeps hitting the side of the index finger, preventing it from rotating. On the right, the missing index finger leaves a gap, which makes it easy for the cube to fall off the hand. Despite these failure cases, Get0 represents a key step forward in embodiment-aware policy design.